Okay, so when I sent you home to do this homework, I said solve these systems of equations using whichever method you preferred. And then I said you'd probably run into some issues. This is exactly the type of problem you're going to run into an issue on. So whoever tried this, what did you try and do? Did you use substitution or elimination?
I used elimination.
Elimination? So what did you...
I just multiplied the top equation with negative.
Okay, so you multiplied the top equation by -2. I like that approach because that's going to give you a -2x1. We'll say it's x sub 1, but we'll say x1. That'll give you -2 of them, then you have +2 and they'll cancel, right? So you're going to have to distribute that through. You'll get a new system. You'll have -2x1, -4x2, and then -8. And then this one is 2x1 plus 4x2 equals negative. Did I copy that down right? I did copy that down right. It was -8? Yeah, so it's -8 again? Yeah. Okay. All right, so that's what you did. And then you add straight down. And this is where you're going to run into a problem. Because when you add these together, you get 0. Plus, and when you add these together, those are the same, but they're opposites, right? So they go away, and you get 0 again. And then you go on this side, and you add straight down, you get -16. And all of your variables have disappeared, right? You have no variables anymore. And basically what you're saying is that 0 is equal to -16. So is 0 equal to -16? No, this is not true, right? So what we're getting here at the end is a statement that doesn't make any sense, right? So this means that the only way that these two lines will hit each other is if 0 can equal -16, which means they can't hit each other, right? Which means they are parallel lines. So there's no solution. So no solution. I'm going to do 65 next. So no solution. These lines are parallel. And remember when we were talking about lines, we had really 3 scenarios. When you're talking about 2 lines, you can have them hit each other, get a single solution. You could have 2 parallel lines, which means you'd have no solution. And then you have a third case where you're talking about the same line right on top of itself. And this would give you an infinite number of solutions. So most of the problems in this homework set, you got 1 solution. But on 61, you actually get no solution. Now 65 is going to be this case. But let's see why 65 is that case. Any questions on this one? Okay. So 65. 65, you have 3x1 minus 6x2 equals -9. And then you have -2x1 plus 4x2 equals 6. Also, this notation with the x sub 1, x sub 2, they're just using that instead of using like x and y. That's a common thing in mathematics to use subscripts. And here's the reason why, just in case you ever wanted to know why we do that. We don't do it just to make it more confusing. But think of it this way. Let's say I had an equation that was like 3x plus 4y plus, what if I had another variable in there? I could call it maybe z. 7z plus, what if I had another variable in there? I could call it, go ahead, what? A. 5a plus, what if I had another variable in there? I could use b. All right, so plus 3b. What if I had 100 variables? What's going to happen? What are you going to run out of? You're going to run out of letters, right? You have 26 letters in the alphabet. You're going to run out of letters, aren't you? Now you may think, well, why would you ever have 100 variables? But there are there's a famous problem that was done when computers first came around. There was a business problem, so a problem that related to business that required solving a system of 400 variables, 400 equations simultaneously. So this is 2 equations, 2 variables. But there was this very famous problem that required solving 400 equations with 400 variables. You can't use A, B, C, you can't use X, Y, Z because you'll run out of letters. So what we do instead is we do 3x sub 1 plus 4x sub 2 plus 7x sub 3 plus 5x sub 4 plus 3x sub 5. Understand? And now I can have as many variables as I want because I'm never going to run out of subscripts. I'm never going to run out of numbers. That's the reason why. It's not just to make math look more confusing. There's actually a purpose for it. So, but we want to just treat this like this is x, this is y. This is x, this is y. All right. Now, for this one, who tried this one? And I want to go with whatever you did. So, who tried it and had a problem? Okay, what did you do? Elimination, I guess, or?
Yeah, I did elimination. I did the top.
Uh-huh.
The top one by 2, the bottom by 3.
Okay, so top one by 2, bottom one by 3, and you didn't even have to use, because this one was negative, you could use a positive 3 here, right? So it worked out. All right, so you multiply through like this, and so you get a new system of equations, and it was 6x1 minus 12x sub 2 equals negative 18, and then you have negative 6x sub 1 and plus 12x sub 2 equals 18, like that. And then when you add down, something very similar happens to what just happened. On the left side, these go away, so you have 0, don't you? And on the right side, you have 0. That means in order for this system to have a solution, you need 0 to equal 0. But 0 is 0, right? The other one was 0 is negative 16. That didn't make sense. This is always true. 0 is always 0. That means that no matter what you pick, if you can find an answer for this one, right? If you can give me an x1 and an x2 that make the first one true, it's guaranteed to make the second one true. Guaranteed. So there are an infinite number of solutions. Now, the way that the book is probably going to want you to put this answer is like this. It's an infinite number of answers, okay? Your x1, okay, so the x value can be any number you want, okay? So pick your x1 however you want. And now you just need to make sure that your x2 that you pick will satisfy this equation, right? It has to satisfy this equation. So what they do is they take this equation and they solve it for x sub 2. So let me take 3x1 minus 6x2 equals negative 9. I'm going to solve for x2. So how about we do this? 3x1 plus 9 equals 6x2. So I moved the negative 9 to the left, move the negative 6x sub 2 to the right. Is that all right? And then divide both sides by 6. So you divide everything by 6. And you should get x sub 2, right, which is what belongs here, should be equal to the left side. So what is that left side if I reduce those fractions? What's this? 1/2 x sub 1 plus 3/2, like that. Now let me see if I can make that make any sense to you, what this is saying, all right? This is saying if you give me an x1 right now, then that number and then plugging x1 into here would give you a solution. So I'm going to plug a number in. I'm going to plug in 1. If I plug in 1 for x1, this will be 1/2 times 1, which is 1/2. What's 1/2 plus 3/2? 4/2, which is 2. So 1, 2 should be a solution. So let's just check it real quick. I've got a bunch of junk up here, but let's just check it. I'm going to go back to these original systems. Just want to check that 1, 2 is going to work. If I plug in 1 here and 2 here, what happens? 1 here, I get 3. 2 here, I get 12. 3 minus 12, negative 9. But it's also going to work here. So plug 1 in here, and you get negative 2. Plug 1 in here, 2 in here, and you get what? Sorry. 8. So negative 2 plus 8 is 6. So it works. This solution is one of infinitely many solutions. If I pick any other x1, like let's say I pick 2, then all I have to do is plug 2 in right there, and it will give me the y coordinate. And that will work in both. Yes?
So when you write it, you can't put it infinite yet, but the...
Well, the book is going to have this, okay? And this may come into play later. So we want to be comfortable writing it in this form. So if you get infinite solutions, then what you need to do is just put x1 here, and then take either equation, doesn't matter which one you use, and solve it for x2, all right? And then plug that in here. So realize that this right here is really x2, but solved. You have to solve for it. Understand? That's the hardest case, I think, of all, because this always confuses students. Like, what the heck is this? This is a representation of the infinite number of answers that you could have.
Is that what you're going to want, or are you okay with just thinking?
I would like for you to be able to do this, yeah. I mean, that's what the book wants. And then, like I said, later on, we're going to actually need to look at this and do something with it. All right. Any other questions on that? That pretty much takes care of the different types of solutions you can get. All right, we got lots to do today. I did input some of your grades. I put in the quiz from last time. Y'all did like one problem, and I've put it back in here, and I'm going to pass out the sign-in sheet. When the sign-in sheet comes to you, just thumb through here and grab yours out of here. You won't see a grade on it, but the grade is online. All right, this is quiz. I counted this as quiz 2. Now, the other one was this is not the word problem. Remember that word problem I gave you? I haven't finished grading that. This was just that one problem that you did in class. So your grade for this will be online. Make sure you sign in also. And then I also put in that grade where, remember I had you grade your own stuff, that thing? Okay, I put that in also. All right, we are going to move on now to a new section. We're going to jump from 4.2 to 4.4. Where is it? Uh-oh. Uh-oh. Oh, no. There we go. Okay. Let's see if I can get in here. All right, we are going to be talking now about matrices and the basic operations of matrices. So you first have to know what a matrix is. And I think what I'm going to do is just kind of define it up here. This is 4.4. I forgot the C in here. Oops. Matrices. Okay, so what is a matrix? A matrix is a collection of numbers. And those numbers can have all sorts of different meanings. But really, matrices is really like a notation that we use to organize data in a more symbolic fashion. All right, so we're going to do some word problems, but let's first just write out what matrices look like. So here is the way we write a matrix. We write a bracket, and then we put numbers inside. So let me just make some up. 2, 3, 5, negative 1. This right here would be a matrices, or a matrix. It has 4 entries, all right? These are called entries, or sometimes elements. Okay? So you see we have four elements or four entries in this matrix? Yes? We call this a 2 by 2 matrix. And what we mean by 2 by 2 is that it's 2 rows and 2 columns. That's 2 rows and 2 columns. Let me give you another matrix. All right, so there's a matrix right there. How many entries in this matrix?
1, 3.
How many numbers do you see there? 3. There's 3 different numbers. Okay, so this one right here had 4 entries or 4 elements. Right here, this one was 4. Here, this one has 3 of them. Right? So this is 3 elements. What is it in terms of a something by something matrix? Now, this is going to be confusing because you can't tell from this. It's either 3 by 1 or 1 by 3, right? So it's 3 by 1. Okay, 3 by 1. And the way to remember this, the way I remember it, is that it's always rows by columns. It's the number of rows you have by the number of columns you have. So I have 3 rows, right, and 1 column. Has anybody ever heard of the RC Cola, the drink RC Cola? That's the way I remember it. The way the numbers appear are RC, rows, columns. Do they even sell RC Cola anymore? Yeah? Okay.
Just called RC now.
Just RC? Okay. All right, so this is a 3 by 1 matrix. Has 3 entries in it. This is also called a column matrix. They call this a column matrix because it's a single column, right? This is not a column matrix because it has more than 1 column, doesn't it? It has 2 columns, 2 rows. I'll give you another example of a matrix. How about this? Bless you. How many entries in that matrix? Looks like 4, right? 4. What is it? What by what? It's 1 by 4. There's 1 row. There are 4 columns, right? So 1 by 4 matrix. And this one is actually called a row matrix. You see why? It's just a single row, right? Now, again, as we proceed through this, we're going to have some meaning, like why we would ever want to mess with a matrix. It'll come together later. But just for now, what we need to do is talk about the basic operations of matrices. So just like we did when we learned numbers, right? When you were learning numbers in grade school, we learned how to add them, subtract them, multiply them, right? We're going to do the same thing here. We're going to take 2 matrices. We're going to see, can we make sense out of addition? Can we make sense out of a subtraction? Can we make sense out of multiplication? Division, we're going to hold off on, all right? We won't actually need division, so not right now. So let's try and add matrices. Adding matrices. Can anybody look at that and just within your own brain, all right, somewhere, just like, does it seem to you like there's any reasonable way to add these together? No? You're shaking your head no, right? Why are you troubled by that? Like, what's troubling about it?
It's not the same. It's not the same.
They don't seem like they're the same size, right? They don't have the same number of elements, but they're not even the same size. Like this one is a what by what? This is a 1 by 2, and I'm trying to add that to a 2 by 2, and there doesn't seem like there's any real way to add them together. Like, would I do like 2 plus 3 or 2 plus 3 and then 3 plus 2, but then what do I do with the 1 and the 5? You know what I'm saying? Like, how do you put these together? And it turns out you can't do this, okay? You can't. Right? To add two matrices together, they have to be the same dimensions. They have to be 2 by 2 and 2 by 2, or 3 by 3 and 3 by 3. So I'm going to put that here. Must have same dimensions. And what I mean by that, dimensions, is the size. You know, if it's n by m, they both have to be. Both. Whatever one is, like rows and columns, they have to match for you to be able to add. They both have to be the same size. So let me come back and give you another one then. How about 3, 5, negative 1. Add that to 7, 0, 5. Now, can I add those together? Seems like there's a reasonable way to add those together, right? They're both, what size? What are the dimensions of those matrices? They're both 3 by 1s, right? They're both 3 by 1, 3 by 1. So I should be able to add them together. As long as they're both the same dimension, we're good. What makes the most sense? That this should equal what? What makes the most sense to you? And I'll tell you whether or not you're right or wrong. 10, 5, 4. 10, 5, 4 makes the most sense? Okay, so what you're doing is you're taking this element, right? Which is the first row, the first column. Well, there's only one column here, right? You're taking the first row, first column, and you're adding it to the first row, first column of this one. Add those two together and you get 10. Now, what about the answer? Is it going to also be a matrix? What do you think? Yes, it actually turns out to be a matrix. So your matrix looks like this. 10, and then the next one would be 5. That's adding the second row, first column, second row, first column. 5 plus 0 is 5. And then the last one, negative 1 and 5 would give you 4. Okay? Does that make sense, matrix addition? Let's do one more that's a little more interesting than 3 by 1. How about this? How about 5, 3, 1, 4, negative 1, 7, plus 2, negative 3, 5, 0, 0, 1, 1, 0, 1. Oops, I put too many. Sorry. Got a little carried away there. Can we do that? Those are both what by what? 2 by 3? That's a 2 by 3. This is a 2 by 3. So we can add them together. So how do you think we're going to add them? How many elements do you think we're going to have in our answer? 6. Our answer is also going to be a 2 by 3. Notice over here our answer was a 3 by 1. Our answer here, when you do addition, your answer should be the same dimension as what you started with. So I need six answers. Here, 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 and here. So what is this first one right here? 7. So you're doing, the first one's here, 5 and 2. Add those together, you get 7. Next one? 0. So can we try and say this in words? This is going to be, the reason I'm doing this, trying to get you to say this in words is because multiplication is a little harder. So if we can get the wording down now, it'll be a little easier with the multiplication. To get 7, I took the first row, first column, right? And I added it to the first row, first column, right? And my result ended up in the first row, first column of my answer. Okay, so when I do the next one right here, I'm going to take the What? First row, second column with, always go row before column. First row, second column. So first row, second column, first row, second column. Add those together, and that's going to be placed into the first row, second column. All right, so that answer you said was 0. This next one, I'm doing the first row, third column with first row, third column, and that's going to go into my first row, third column. Just want to get the language right here. Y'all okay with that? What does that add up to be? 6, and then the rest we'll put in, right? 4, -1, 8. Any questions on that? Vector addition, I'm sorry. I'm in the wrong class.
Do you always read it left to right, top to bottom?
What do you mean?
When you say first row, like when you
I'm always going to say row before column,
right,
but left to right, yes, columns will always be from left to right. Rows will always be from top down. Yes. Good question. All right, let's try subtraction. How do you think subtraction changes things? Not much, actually. We still have the same properties as we do with addition. We have to have the same dimensions. But you're just going to subtract instead of add. So let's do a little 2 by 2 here, 3, 5, 1, 0. Let's subtract from that 2, 7, 1, 9. I can subtract these, can't I?
Yes.
They're same dimensions, 2 by 2. So we are going to have here, forget the wording, just give me the numbers. 1, -2, 0, and -9. Good. So you're taking 3 and you're subtracting 2. 5, taking away 7, that goes here. 1, taking away 1, that's 0. 0, take away 9, -9. Good? Okay. Now, I think addition and subtraction are pretty straightforward. Now what we're going to do is the next operation. This is called scalar multiplication. So for scalar multiplication, you're going to have something that looks like this. What if I take a matrix? Let's just do 3, 2, 1, 5, 7, -5. I just gave you a little what by what matrix there? 2 by 3 matrix. And I want to multiply it, right? But I want to multiply it by what we call a scalar. And a scalar is just a number. So I want to scale this matrix. And all that means is I'm going to put a number out here. And I get to pick the number, so I'm going to put 4. So 4 times this matrix. What do you think that means I do? 4 times every element. Every element gets multiplied by 4. So we would get a new matrix. It would still be a 2 by 3, but it will become now what? 4 times 3, 12. 4 times 2, 8. 4 times 1, 4. 4 times 5, 20. 4 times 7, 28. And 4 times -5, -20. That's scalar multiplication. Seems straightforward? If this was a -4, it would just change these, all these signs would change, right? All right. Now let's get to the difficult one. Matrix multiplication. And what I mean here is a matrix times a matrix. This was not a matrix times a matrix. This was a number times a matrix, right? We say scalar. That number right here is called our scalar. We're scaling it. We're making it bigger or smaller. That's what it means to scale something. So this basically scaled this, made everything grow by a factor of 4. But what does it mean to take 2 matrices and multiply them together? So y'all ready? This is where it gets a little messy. right, so I'm going to start off with a matrix, two matrices that have the same size. And it makes sense, I think, I hope to you, that when you multiply these two together, that your answer should probably be a 2 by 2. Okay, but as you're about to see, it's going to be weird because you can do things that don't seem natural. I'm going to write here underneath this 2 by 2. And here 2 by 2. Okay? When you're trying to figure out matrix multiplication, here's what you have to do, all right? First of all, in order for you to even be able to do it, all right, for you to even be able to multiply two matrices together, these two numbers must match. Those must match. In other words, the number of columns of the first matrix must be equal to the number of rows in the second matrix. You have to have that to be able to multiply two matrices together. Now, your answer, okay, is going to be a matrix here. The dimensions of that matrix actually come from the two outside numbers. So you see this? 2 by, and you see this 2? That tells you how big your matrix output's going to be. I know, just let me do this example, then I'll do another one, and then after we do a few, you'll see, hopefully, how you can catch on to this. All right, so I know that my answer is going to be 2 by 2, right? Because I told you that's what it's going to be. The question is, what are the entries? I should have 4 entries, right? So how do we figure out this first entry? What are we going to multiply, though? 5 and 2? It seems like that would be it, right? It seems like it would just be 5 times 2, and that goes here. And then maybe the next one's these two. It's not, though. And that's why this is difficult, all right? So tell me about this answer right here. In words, that's the what? It's the first row, first column, right? This is, I'm going to do it this way. This is row 1, column 1. Do you agree? That's the position of this? Yes? So how you get that number is by going over here and taking the first row here and multiplying it times the first column here. Because it's row 1, column 1, you're going to take row 1, column 1. You with me? And watch the way I do this. I'm going to write them down separately so you can kind of see them. I'm taking the column 1, or sorry, row 1, and here's column 1, 5, 1. I'm kind of doing this like scratch work on the side. This is row 1, column 1. And what I'm going to do is 2 times 5, which is 2 times 5, I'll just write it down, plus 3 times 1. And then I put this together. So what's 2 times 5? 10. And then plus 3, which is 13. That's the number that goes here. I told you it was weird, right? Have I delivered on that question? 2 times 5 plus 3 times 1. Put those together, that goes here. Let's just try another one. How about this one? Tell me about its position in words. It's row 1, column 2. This is row 1, column 2. So I'm now going to just forget this. I already did all that work. I'm going to come over here. I'm going to look at row 1 here and column 2 instead of column 1. And I'm going to write them down. Row 1 is still 2, 3. And column 2, was what? What's column 2? 2, 3. And now tell me how I do this multiplication. 2 times 2 plus 3 times 3. And that gives you 4 plus 9 is 13 again? That's just coincidence, okay? It's not always going to happen that way. Understand? I've seen probably a dozen ways to teach matrix multiplication. They're all equally great. This is the way that I've always done it. Hopefully it makes sense to you. The book, I'm sure, shows something a little different. Tell me about this bottom left position. Where is it in the matrix? Row 2, column 1, isn't it? So I'm going to go grab row 2 and column 1 over there, and I'm going to do the same thing I did here. Are you kind of catching on a little bit? Okay. It's going to get a little more interesting when these matrices aren't both 2 by 2s. You'll see how it's going to get a little tricky. So now I'm doing row 2, column 1. So I write down row 2, that's 5, 1. And I write down column 1, which is 5, 1 again, right? And when I do this multiplication, 5 times 5 plus 1 times 1, so 26. This is this one. What? I only have 30 minutes remaining? Why? I had it plugged in for a long time. Turn my brightness down. Oh yeah, because that has no impact on what it looks like up there. All right. What's the bottom right one? Does anyone have the answer yet? 13. It's row 2, column 2. So you're going to be doing, let's see if we can do it without writing it down. Do you think you can? It's row 2, column 2. So 5 times 2, 10, plus 1 times 3, so 13. There's your result. What do y'all think? It's a little weird, huh? Let's do something different that's not 2 by 2. And you'll see how this can get kind of messy. Now, if I asked you to add these together, could you add them? You cannot add these together. Can you multiply these together, though? Let's see. Tell me what they are. This is a what by what? 3 by 2. This one is a 2 by 1. Do these inside ones match? Yes. That means my answer is going to be the outside ones. So my answer is going to be a, what? 3 by 1, which looks like this. It'll have 3 entries. Do y'all agree? Any questions on that? Okay. Tell me about this first entry. Its position in here is what? Row 1, column 1, right? Row 1, column 1 is this one? Okay, so I'm going to go over here. I'm going to grab row 1 and multiply times column 1 on that one. So row 1 is here, column 1 is here. So what do you get? This. So 3 times 7, right, which is 21, plus 1 times negative 2. 3 times 7 plus 1 times negative 2. This should be 27. Take away 2, 25. Go with me? Yes? No? I did row 1 is this one, right? Column 1 is this one. So I'm going to go 3 times 7 plus 1 times negative 2. Oh, did I? Hold on. Oops. 19. That's why y'all were looking at me like I'm crazy. Well, I guess my laptop wasn't going to last 30 minutes. Oh, well. That was a quick 30 minutes, huh? Class is almost over now. All right. Sorry about that. 21 minus 2 is 19. That better? Now that I did my arithmetic correctly? Is that better? Now I did? Okay, thank you. All right. I understand. Now this next one is going to be what? Row 2, column 1 again, right? So I'm going to take row 2, column 1. Let's see if I can do my math correctly here. 2 times 7, 14. Negative 4 times negative 2 is 8. And you're adding them, right? So 22. This was 19. This is 22. And then finally, the last one will be row 3, column 1. So row 3 is 5, 0. And you're multiplying it times column 1, which is here. So 35 plus nothing. So just 35. Okay. What do y'all think? That's matrix multiplication. Now, just so you know, in the book, when you're multiplying two matrices, they will not put the symbol here. So if you see this and this, they're implying multiplication. There is an implied multiplication symbol there. Now, if it's addition or subtraction, they will put the symbol. All right? All right, so I'm going to give you a word problem. I was going to project it, but I can't. All right, so I'm going to give you two matrices. Matrix A is this matrix right here. I'm going to leave a space here on purpose. It's the matrix, where is it here? $45,000, and then $106,000. $77,000 and $22,000. Close that off. And then matrix B over here is 190,000, 266,000, 345,000, and finally 276,000. Now, let me explain to you what these are. This matrix here represents the sales in August 2017. This is the sales in September of 2017. Okay? Even though September is not over, we're just making this problem up. And this matrix is comparing two different salespeople. All right, so I'm going to put here to the left, and I'm going to do it in a different color. This will be Mr. J, and this will be Mr. T. Mr. T and Mr. J, whoever they're, John and Tim or whatever. And this is his sales. These are car salesmen. And Mr. J, this is the sales in sedans. And this is his sales in SUVs. Understand? So how much How much in SUV sales did Mr. T have for August? $22,000 in SUV sales, right? So you see how that matrix kind of summarizes, that little set of numbers summarizes what's happening in August, right? Same thing here, Mr. J and Mr. T. And here we have sedans and SUVs. So I have a question for you now. What does A plus B represent? What's that? How do you mean? Elaborate. Total sales of something, not of how much each of them sold.
How much sedans Mr. J sold?
How much Mr. J sold? Total, right? Total sedans and SUVs. But is it going to be together or they're going to be separate, right? Because our answer should be what size matrix? It should be a 2 by 2, right? So let's go ahead and add these. Let's do A plus B. What is A plus B? A plus B would be a 2 by 2 matrix. And we would be taking just the first one here and the first one here, right? So 190,000 plus 45,000 is what? 235,000. And then let's do the top right corner. So 345 and 77. What's that? 75, 400. Is that 412? 422. 422. And then bottom left, 372, I believe. In the bottom right, 298. Y'all can check my math. This is just arithmetic. My brain turns off when it comes to arithmetic. Okay? That would be our matrix. So what would this 235,000 represent? Total sales by Mr. T of sedans in both August, Mr. J, sorry, of Mr. J in both August and September, right? This would be his total sales, Mr. J's total sales of SUVs in both the months of August and September. So what you do is, if you're running a business, what you can do is create like an Excel spreadsheet where you put in the data, and then you're basically just adding matrices to get like total sales. How about this? What would B minus A represent? It would be the difference in their sales, but can you elaborate a little more on that? Yeah, it's the difference, right? But between which months? September and August, yes? See, subtraction doesn't order matter, right? So let's just start trying to get B minus A. B minus A, and let's just start with B minus A. We would have to do this one minus the 45,000, right? So what's 190 minus 45,000? 145,000? Okay. Let's see if there's any here that... Yeah, do the bottom left one. How about, well, these are all bigger, aren't they? Oh, well. I was hoping to get a negative answer here. None of these are going to be negative, are they? Oh, well.
Just do it the other way.
Yeah, if you did A minus B, they would all be negative. But I wanted to have some mixed. Let me just make up my own number here. Let's just say that this was negative 30,000. I know it's not, okay? I know it's not, but what would this mean? This would mean Mr. J, his sales of sedans did what from August to September? They increased, right? Because what this is doing is it's taking the difference. Look at his sales in September. They were 190. Look at his sales here. They were 45, right? So they went up. They went up, which means that that's a positive number. But if this became a negative number, that means the sales would have gone down. See that? That would be something as, you know, an employer, you would want to look at your salespeople, print out their matrix, and be like, hey, you know, anytime you see some negatives there, you're like, hey, you know, what's going on? You need to hit those SUVs a little harder or something. Whatever. But you can just tell by the signs within the matrix what's going on, whether or not you're having increase or decrease. All right, what about A times B? What about AB? Does it have any meaning? Does it have any meaning at all to us? In this real world situation, we got two salespeople, you got their sales in different months here for different styles of cars. What would AB actually mean? So what would AB look like? It would be a what by what? It would be a 2 by 2, wouldn't it? So A times B would be matrix multiplication, would be a 2 by 2. Now let's just try and figure out what that top left corner would be, like this right here. This would be row 1, column 1, wouldn't it? And that means you're going to take the first row here and multiply it times the first column here, right? And so you're going to take 45,000 times what? Taking the first row here times the first column here. So it'd be 45,000 times 190,000 plus 77,000 times 266,000. And you're multiplying those, or adding those together and getting some huge number, right? Does that number have any meaning? No, right? You're multiplying their sales together, adding it. It doesn't have any real meaning in the real world here for this problem. Could you do it? You could, but it wouldn't matter. Yes?
And multiplication, why would we do it like just simple 45 and then the answer 77?
Why wouldn't you? Because that type of multiplication, you would only be able to multiply matrices that have the same dimensions. You could only do a 2 by 2 and only a 3 by 3, only a 4 by 4, right? That's the only thing you could ever do with matrix multiplication. You wouldn't be able to do some weird combination. Like we did a 3 by 2, and we did that times at the 2 by 1, I think, just a little while ago, or maybe it was something else, I don't know. But you could, with matrix multiplication, you can do some different dimension matrices multiplied together. And there are problems where these numbers actually have meaning, like the multiplication has meaning. I haven't gotten to that, but. Okay, let's try one that has some meaning to it. Did that sign-in sheet get around everyone? Can y'all hear that? Somebody's having fun. Other than us. I had a student give me these markers like last semester. They're like, hey, I got you some markers, sir. And they're really good. They show up really, really nice on the board. But man, they're hard to erase. All right, labor costs. This is an example, all right? A factory produces water skis, okay? Water skis. they require 5 hours of labor. In assembly. That's what they're using here, yeah. Assembly department. And 1.5 hours in finishing department. Okay, so you've got these skis. We're going to manufacture these. And we first have to put them together. So you get all the raw materials. In one area of our manufacturing plant, we're going to assemble the skis. And that takes 5 hours to do per ski. Then after they get through with the assembly, they go to the finishing department. That's where they buff it and they make sure there's nothing, no little pieces of plastic hanging off the edge. And they finish it out, and then they pack it up and they get it ready for sale. That takes an hour and a half per set of skis to do that. Now, the costs in each department for labor are different. So yes?
In the matrices, like say, can you get a fraction? I mean,
Can you have fractions in your matrix? Oh yeah, absolutely.
is it better to use fractions or decimals?
Oh, that's really up to you. I mean, whatever you're more comfortable with.
Is it the same as when you're multiplying the matrices? Like how would you do that? Like multiply straight across or make sure you have the same denominator?
Well, with multiplication of fractions, you don't have to worry about the denominators, but adding, you would have to get common denominators, yes. So maybe go to a decimal. Yeah. Okay, so no. Okay, so the assembly workers cost $9 an hour. And finishing workers cost $13 per hour. Don't ask me why, I just made those numbers up. The finishing workers get paid more. What we want to come up with now is what is the cost for this company to manufacture one set of skis. So find cost to make one set of skis. Is that the way you spell skis? I guess so, huh? Seems wrong. But that's skies, isn't it? Is it also skis? I don't know. Who cares, right? It's English. It's English. So how would you get this total cost?
Well, you said 5 hours of labor.
5 hours labor.
$9 per
At how much?
$9.
$9 per hour.
So it's 40.
So, right, 45 bucks. And then, after it gets through with the assembly, it's got to